So I'll record and I will start by sharing my screen again. Okay, so now you can all see my screen, correct? All of you can see the
Yes, sir.
screen, right? So let me then formally begin the course Computational Finance. This is a continuation of the course I taught last semester, Quantitative Finance. So all the definitions and standard models we will be assuming. Sometimes we will quickly review things, but I will assume that you have already studied them. As I have already told you, our textbook for this course is Computational Methods in Finance by Ali Hirsa. So all of you have now downloaded the book.
Yes, sir.
Yes, yes.
Because as you can see from the course outline, it is direct subset of the contents of the book. So I'll be following this section by section. So it's a very easy way to deal with the course if you follow the book. So we will start with the basics. The basic things are here. Stochastic process. Well, I'm not going to give you lectures on stochastic process in general, but we are going to talk about some specific issues and then some specific examples, which are common in financial models. And then move on to risk neutral pricing, which will be sort of a revision from last term. But because it's a different book, a little bit of different notation, so we will go through that so that we are on the same page in terms of conventions and notation. Then the basic primary part of the course starts from chapter 2, where we first deal with transform techniques. Then chapter 3 talks about finite difference methods. I don't know whether you have ever done finite difference methods. Probably in your BStat first year or in your BSc first year, second year, somewhere, there should have been a numerical analysis course where
Yes, sir.
you learned about Newton-Raphson, Gauss-Seidel-Newton methods, things like that, okay? So finite difference method is essentially the same thing applied in financial issues particularly. So we will continue with finite difference methods and then use them in chapter 4 and 5 to solve the stochastic PDEs and PIDEs. So PDEs are for continuous models. We have learned that we start with standard Black-Scholes PDE. And when there are jumps like Levy process models, then we have PIDE, integral differential equation. That also we have introduced last term. So now we will sort of review and then look at the numerical analysis of those equations, because those equations are notoriously complicated to handle analytically. We will do numerical approximation. And then we will go to simulation methods. When everything else fails, we take recourse to simulation methods. And that will be the content in chapter 6. So that is, as I said, the basic coverage of the course, which I definitely want to do. The filtering and parameter estimation, which I have taken from the second part of the book, omitting chapter 7, because I thought that would be too much. As Subhajyoti has already pointed out, the syllabus looks pretty long. But I have kept this one because I thought learning about Kalman filter is very important. And I checked that in your time series course, I think Kalman filter wasn't covered. There wasn't time. So I thought that this would be a good finishing to the course here. But I do admit, which is strategically wrong of me, I do admit that the syllabus is slightly long. So regarding examination and evaluation, we will probably decide on a subset later on. So that we can discuss later. But in terms of coverage, I do understand that there is a little bit of extra material here, but we will see. We will see as we go along. Okay. And you already have the evaluation plan also, I think, that I have posted on the classroom. So we will have physical examinations this term, I am told. I was also told that sometime in the next month, the physical classrooms will also be ready for classes. But I will be continuing online at least throughout February. So in March, we will rethink and decide about whether we should move to the classroom. But anyway, the examinations will be usual pen and paper examinations in the classroom. So the mid-sem and the end-sem will have 20% and 40% weightage. Usual examinations. So closed book, closed notes, conventional exam, which you prefer. And other 40% marks is reserved for assignments. Again, I will have a research reading assignment that will be 15%. Another 15% will be devoted to an extension to whatever paper you are reading. So you have to select your paper strategically. So you both make a critical report on the paper as well as make an extension to the numerical work done in the paper. And of course, it goes without saying that the paper has to be a computational finance paper. So if it's a pure theory paper, then you have to devise your numerical work on your own. If it's a computational finance paper with computation algorithms, then you will be asked to do an extension to the algorithm. So that will be assignments 1 and 2. And finally, there will be a conventional problem solving assignment worth 10%. Any questions or doubts here? Okay, so hopefully all of this is absolutely clear. So now let me start with the introductory material. So when I was going through Hirsa's book again for teaching you this term, because I taught it once last year, and this is my second time doing the computational finance course. I was going through the preface to the book, and I came across a very interesting quotation. This quotation is from the autobiography by Professor Richard Bellman, and the name of the autobiography is Eye of the Hurricane. So Richard Bellman is an extremely famous mathematician. In fact, if any of you know anything about dynamic optimization, then you must have come across the term Bellman's optimality principle. So that is considered as the cornerstone of any dynamic programming problem or dynamic programming algorithm. So it is almost as powerful as the central limit theorem in optimization literature. So this is Richard Bellman, and he wrote, in fact, once I saw this paragraph, I felt intrigued and I have started reading this autobiography actually, Eye of the Hurricane. It's extremely well written. Bellman happens to be also a good writer in simple English. So it's not only a great mathematician, he has passed away a long time back. He was not only a great mathematician, he was also actually a good writer. So, okay. So let me just read this out, this paragraph from page 185 of this book, Eye of the Hurricane. So he says that in order to make any progress, it is necessary to think of approximate techniques and above all, numerical algorithms. And with a gap, once again, what became a major endeavor of mine, the computational solution of complex functional equations, that was his theoretical interest, research interest. So was entered into quite diffidently. So diffidently means with a lot of hesitance. Okay, so he was hesitant to enter into numerical or computational area. He says, I had never been interested in numerical analysis up to that point. Like most mathematicians of my generation, his generation, I had been brought up to scorn this utilitarian activity. This is still true for most of the ISI fraternity that you know, that people think that doing pure theory is the only thing worth doing. Anything numerical or computational is grade B. Numerical solution was considered the last resort of an incompetent mathematician. So all of these sentences, I think, sounds extremely familiar to many of us. Then Bellman says the opposite, of course, is true. Once working in this area, it is very quickly realized that far more ability and sophistication is required to obtain a numerical solution than to establish the usual existence and uniqueness theorems. It is far more difficult to obtain an effective algorithm than one that stops with a demonstration of validity. And he finishes by saying that the final goal of any scientific theory must be the derivation of numbers. Any comments at this point? Can you all hear me clearly, by the way?
Yes, sir.
Yeah. So are there any comments on this? Because I found this paragraph very interesting on several dimensions. First of all, the sentiment, in the first part of the paragraph, the sentiment prevalent at that time still seems quite prevalent here in ISI. And the second part is also a very practical and very realistic issue that I have faced all through my career, because we were not really taught computation very seriously. Computation was actually considered inferior. So we spent a lot of time on existence and uniqueness theorems, but very little on computation. But this quotation actually written back in the 1970s, when I was a very little child, and even then Bellman says that it requires a lot of effort and sophistication to come up with numerical solutions. And the quotation is just prima facie not only important in the finance context, but probably relevant in many other contexts. That's why I thought that I would share this with you. This has got nothing to do with what we are going to lecture on, but this seems to be a very good thought and very good principle in general. Okay, so going back to the content of the book, Hirsa says that, okay, so these are some sentences picked up from the preface, which I thought are relevant to the style of the course that we are going to do this semester, because the style is important. Last semester, we were focusing more on mathematical models, on theorems, conventional theorems. This term, our focus will be much less on theorems. In fact, we will not even bother with formal proofs of any theorems. Our focus will be completely on finding out algorithms. So the final target is, in any context, for any model, we want to get to the algorithm which can be run on a computer. So that's why Hirsa says that advances in quantitative finance would have been impossible without utilizing computational or numerical techniques. And it is hard for you to probably appreciate, but the computational power has changed a lot in one generation. So when we were students, the kind of computational power we had access to, even being in ISI, which is one of the more advanced institutes in the country, would be, a matter of humor if I tell you that our computers had hard disk size of 5 MB. You actually heard that right. It is 5 MB. I'm talking about just MB. It would be very hard for you to believe that, but that's what we started with. So the whole game has changed with development of computing ability, computing technology. And of course, now we are very confident of computing almost any model. If you can write it down, you can compute it. So in most applications and physical phenomena, so it goes across finance, physics, chemistry, and other sciences, we are actually in search of a solution that happens to be an approximation of the true solution, because the true model, the true solution is too complicated to handle. Not only analytically it's impossible in most of the cases, even numerically, to get to a reasonable solution, to a reasonable set of numbers, we have to make approximations. So as a result, some sort of computational method or technique or numerical procedure is a must. Particularly in quantitative finance, aside from a very few canonical cases, which has analytical or semi-analytical solution, most of the time we typically wind up with an approximation. Even in the later part of the course last semester, we have seen models where analytical solutions were either not available or extremely difficult to arrive at. So this term we will focus more on computational algorithms rather than spending time on finding analytical results, which are most of the time not available in any case. So as financial products become more complex, the contracts are becoming more and more complex. So whatever complicated thought pattern an investor can think of, it can be translated to a contract now. We have seen a lot of complicated contracts last term. So as products become more complex, quantitative analysts, financial engineers, so now they are called financial engineers, the algorithm designers, and others in the financial industry now require robust techniques for numerical solutions. So we will not only look for numerical solutions, we will also look for robustness of those techniques. Robustness are defined in terms of various parameters, which we will explain, about rate of convergence, about radius of convergence, whether the solutions are stable under perturbation, things like that. So if you have done a differential equation course with initial value problems, etc., then you will know that perturbation techniques are quite common in those things. So do you know this? Just a quick query. So the initial value problems in differential equation, is that familiar?
Yes, sir.
So you know perturbation techniques also, or only classical solutions were done?
No, only classical solutions.
Classical solutions. Okay, so that is the problem. You see, the classical solutions are only for very nice canonical models, which can be completely solved analytically. But most of the time we are not that lucky. We get differential equations, we can set up the differential equation, but we can see that we have to use other kind of techniques. Okay, so we'll talk about that most of the time in this course, so that's all right. Okay, so Hirsa says that he has been quite informal about the theory. And as example, he cites that he has used the ethos lemma for semi-martingales. Semi-martingales are obviously an abstract object, which we have defined last term in an informal way. So he has used ethos lemma for semi-martingales without defining semi-martingales. So first up, he admits to being informal because he wants to focus more on computation than on the theoretical nitty-gritties. He has also used Girsanov's theorem without stating the theorem. So the book has no statement of the Girsanov theorem, but Girsanov's theorem is used in different parts. So he says that he has been quite informal about it, and the focus is different. Okay, and again, as short outline of the book, the outline of the book is same as the outline of the syllabus, that in chapter 1, it is principally relating to the construction of the characteristic function of the stochastic processes. So basically those stochastic processes which are most commonly used in finance. So he starts with a review of the characteristic functions, and then he shows how to use the characteristic functions to generate the moments, because most of the analysis will be done through the moments. Chapter 2 to 6, 2, 3, 4, 5, 6 are about the computational approaches. As I said, chapter 2 talks about the transform techniques or the numerical approximation techniques like finite difference. Then it goes to use the finite difference methods for solving the PDEs and the PIDs in chapters 4 and 5. And of course, as I said, The method of last resort, Monte Carlo simulation, is discussed in chapter 6. So that is more or less the outline of my syllabus also, which I showed you here in more detail. So this syllabus is what we are planning to cover. In addition, we are also planning to cover filtering, but we'll see. So that's more or less all about the outline. So do you want to ask me anything at this stage, or should I move on to chapter 1?
Sir, I have a question.
Yes,
Actually, I did not take the previous course, and I am planning to take this course. So, is that feasible?
it is feasible, but it is going to be a little bit difficult. But you were in some of the lectures last term, if I am remembering.
Yes, sir. I was
Right?
there. Yes.
Uh, so you know the material to some extent, correct?
Yes.
And you also have seen the lecture videos and the textbooks.
Yes, sir. I was going through them.
Then it should not be a problem. In fact, I
Okay.
saw 2 new names in the uh, in the classroom. Let me see. There were 2 new names here: Bhargav Kakoti and which was the Rajesh Kormukar. So any one of you are here, Bhargav Kakoti or Rajesh Kormukar?
No, sir, they are not here.
They are not here, right? Yeah, I can see that too. So then, so I don't know why they entered, but maybe just to look at the syllabus. But anyway, so Arindam, I don't think it should be a problem unless there is a technical issue like is quantitative finance officially a prerequisite of computational finance?
No, I looked at the brochure. It's not.
Then there is no problem. You may have to go back and look at the lecture videos again, talk to your classmates. It should be fine. But as I said, I'm going to assume that material. So you have to be conversant with the material.
Okay.
Fine, good. So now let me then move on to chapter 1 if there are no other questions or comments at this stage. Before I begin, just one aside. This I was discussing with Abhinandan earlier, that whether there will be special lectures in this course also, like in the last term. My answer is I'm not sure yet, because in quantitative finance, because I work in that area, I have been working in that area for quite some time. There are collaborators and friends and students whom I asked. My knowledge in computational finance is extremely limited. In fact, the Omega is practically Ali Hirsa and maybe a few other books. So last term I taught it for the first time, and this is my second round, and I'm still learning. I'm still learning at the very initial stages. So I don't have collaborators in this area, so I don't know whether I will be having special lectures, but I would like to have 1 or 2 people who can give you a broader perspective of this topic, because I don't have a perspective of this topic yet. As I said, I don't work in this area, but it's not fixed, so we will get to know once there is an update. Okay then. So if there are no other comments, I will start with chapter 1. I don't know whether you have access to the notes subdirectory in the classroom. Do you? So there is a Google.
Yes, sir, we can access them.
You can access them. So you can see that I have become more technically savvy, and I have now prepared some lecture notes. Typed lecture notes, because last term it was handwritten, scanned. So I tried to be a little bit more tech savvy, and I have prepared some lecture notes, 1 Word file for each chapter, which you should be able to see and which I will be using in this class. Can you all access them?
Yes, sir.
Yeah. So again, this is subset of the book, and I will still need you to go through the book itself, because there will be a lot of things which I will omit, but will be part of the syllabus. I will tell you, of course, won't be any surprises, but I am not going to talk about each and every detail, and I will refer to the book from time to time for the gaps. So I will start chapter 1 today. And as I already mentioned, chapter 1 is about stochastic processes and risk neutral pricing. And what we will do in this chapter is we will review, first of all, the standard financial processes that are common. Most of them will be familiar because we have done them last term. So processes that are commonly used to model assets in different markets and how derivative contracts can be valued. So that issue we have seen at least in a theoretical manner last term, so that is already known. We will also review characteristic functions of the standard distributions, all the popular distributions, and particularly those which are important for us in closed form wherever they are available. Again, this is known to you. You have all learned characteristic functions, but we will have a quick review of it. Then we will focus on the commonly used stochastic processes for our financial asset modeling. And finally, we will talk about the stochastic differential equations where a closed form exists, because we will also point out situations where closed form equations do not exist. So equations may be implicit. And that's where the simulation methods will come into play. But first we will start with the simple ones which are analytically solvable. Great. Then we'll get into those which can be written out explicitly, but has to be numerically solved. Not bad. And finally, we'll get to situations where even the equations cannot be written out explicitly, but we will still have simulation to tackle them. So those models we will review in the first chapter. So the first section is characteristic function. The notation might be a little different from whatever probability textbook you have studied earlier. The notation here will be the probability density functions will be small f. The characteristic function will be typically this symbol phi or psi, the Greek alphabets. And first of all, I don't know whether you have explicitly learned this before, that characteristic function is nothing but Fourier transform. Is this known to all of you? You all know characteristic function, but do you know that it is just the Fourier transform?
Yes, sir.
Yeah. Okay, good. So the section actually starts with the definition of the Fourier transform and its inverse. So for any function fx, the Fourier transform is defined as this. Phi v is this e to the power I nu z fx dx over the whole of the real line. So first up, we are focusing only on real valued random variables, only on the real line. Most of the time we will talk about one-dimensional models. So many of the theoretical complications are as yet not here. So our Fourier transform is defined like this, phi v, and having the Fourier transform of a function, if I know phi v, I can also recover fx through the inverse Fourier transform. So the inverse Fourier transform gives me fx as 1 by 2 pi, again integral e to the power minus I nu x, phi nu d nu. So this is already known. I'm just doing recap. And of course, now we come to the characteristic function, the probability object. So if f is a PDF, probability density function of a random variable x, its Fourier transform is actually called the characteristic function. So same definition as the Fourier transform. For a PDF, it is called the characteristic function, which I can also symbolically write as expectation of this transformation e to the power I nu x. Because in probability, this is our familiar language. We talk about moments. So characteristic function itself is a moment of a transformation. And again, I can recover my PDF from the characteristic function through the inverse transform. So this is our basic tool. And now we go ahead with this tool to also talk about the cumulative distribution function, because normally we are also very interested in finding what the CDF is. So CDF, the standard notation is capital F. And we know that capital F is just integral up to small x, f tau d tau. So probability x less than or equal to x. And if I now insert the inverse Fourier transform here, I can see that I can also get to the CDF. I can also get to capital F from phi function through this double integral. So inside I had f tau, f eta. So that f eta can be recovered from the characteristic function using the inverse Fourier transform. So I have a double integral in my hand if I want to find out the CDF from characteristic function. Okay, so before I get into this, why am I actually interested in doing this, doing it this way? Why can't I directly talk about the PDF or CDF? Can you tell me why is characteristic function important or the inverse transformation important? Because an obvious answer would be just look at the density, integrate it, and get the distribution function. Anyone? Why do I need to talk about this at all? You have all studied characteristic function in probability courses. You may also have used it in your statistics courses. Why do you need to study it, apart from theoretical reasons?
Discrete time computation will be easier,
Why is it easier?
and because I think that discrete time computations will be much more efficient.
You think or you know?
I think.
Well, that is not a good answer on two counts. One is that you should know because it can be, demonstrated which one is more efficient. And the other count is that is not a real reason of using the characteristic function, because if I have the density function, why should I bother with a complex integral? It is a complex integral after all. Why do I need to talk about
For
characteristic?
independent random variables, the
Okay,
sum can
why?
be written as product of characteristic functions.
Huh? Come again?
The characteristic function of the sum of independent random variables can be written as the product of the individual characteristic functions. So that might be helpful for computational purpose.
But suppose I give you the density function, will it not do?
Computation might not be easier all the time because you have to still compute the density of the sum. The
Huh.
characteristic function,
Okay.
it's already like a product.
Okay, and then?
And as we know that characteristic function uniquely determines the distribution.
I think now you are coming to the point. So characteristic function uniquely determines the distribution. So I think there lies the more important reason for handling characteristic function. Can you now tell me what the most important reason is? What you said about characteristic functions is also true about moment generating functions, correct?
Yes.
So now can you guess what is the most important reason?
So we can uniquely determine the moments of a distribution if we know the characteristic function.
But so can I if I have the density function, right?
Yes, but you have to compute an integral of.
Here also you have to compute integrals. In fact, they are.
But that's one time, only one time. If you just compute the characteristic function, then all the moments can be calculated by just differentiating the characteristic function.
Right. Then you have to do numerical differentiation, which is almost as complicated as integration. So what you are saying is correct. I'm not saying it is wrong, but that is not the bigger reason. The bigger reason is actually more basic, more fundamental. You see, in actual data situations, you are given some data, and what you do, what you used to do in your undergraduate days was to fit a probability distribution to the data using chi-square techniques, etc. That's what we have all learned to do. That you fit a normal distribution, you fit a binomial distribution to a given data, etc., etc. So the real question is, when you are given a data or when you are studying an actual situation, you don't know what the density function or the distribution function is. What you can estimate are the moments from the data itself. And those moments in turn will help you to determine the density and the distribution function. And that is where the characteristic function or the moment generating function plays an important role. Because as you correctly said, characteristic functions generate the moments. But you can reverse this statement also, that if I know all the moments, I can reconstruct, I can recover the characteristic function, and hence I can uniquely find the density function, because there is a one-to-one correspondence there. If you look at the usual version of proof for the central limit theorems, they also are based on this fact, that I expand characteristic functions and then I show that higher moment terms are all negligible. So it's basically that story, that when you are given a data, what you can directly compute are the moments. And from the moments, you try to go back to the density and the distribution function. So characteristic function or moment generating functions are a very efficient way of doing that. Is that clear? Am I making sense?
Yes, sir.
So have you ever done this? No, I don't think you have done this, because if you had, then you would have come up with the answer. You have never estimated distribution functions or density functions through characteristic or moment generating functions, right?
No, sir.
No, but it's a very efficient way of doing things. That's where numerical analysis comes into the picture. It's actually a very efficient way. Of course, there are some issues like radius of convergence. You know that, correct? The radius of convergence question.
Yes, sir.
For moment generating function, it's a significant issue. But even with that, because we have this unique one-to-one correspondence between characteristic function and the distribution function or density function, starting from moments, this is a very good path. And that is where this thing is so important. Okay. So let me continue. So we were at this point where we see that the cumulative distribution function can be recovered through a double integration of this characteristic function. I need a double integration. So that is not good, because double integration means numerical process applied twice. So all the approximation errors being accumulated. So what we really want is, we want to find capital F directly from phi, but avoiding a double integration. That is always better. So what we do is, this is a trick that we can use. What we use is a Fourier transform of not capital F. But Fourier transform of e to the power minus alpha x capital F. This e to the power minus alpha x is called a damping factor. Take alpha positive. This is called a damping factor. And you look at e to the power minus alpha x fx instead of only fx. So now, using this notation and definitions here, look at this integral. So minus infinity to infinity e to the power iux e to the power minus alpha x fx dx. So this is an integral in the same vein as the Fourier transform of capital F, but not the original capital F, with an additional term inserted here. So I can write it as e to the power minus alpha minus iu x fx dx. So I collect the exponential terms inside. Now use integration by parts. So if you use integration by parts here, you can check that the first term will vanish. The first term will vanish, and what we will be left with is the following, because in the second term I will be differentiating capital F. So inside I get small f, and this exponent comes out in the denominator. So this integral will be transformed to, finally, through this path, this divisor here, integral e to the power I u plus I alpha times x fx dx. So this u plus I alpha has been put inside a box here to highlight that if I think of this whole variable as an argument in the Fourier transform definition, then this integral is nothing but phi evaluated at u plus I alpha. You see, the usual phi is this integral where the exponent has I nu x. So I nu was the multiplier of x. Instead of I nu, now I have u plus I alpha. So this was phi nu by definition. So it is phi u plus I alpha using the same definition. So this integral becomes phi u plus I alpha and divided by alpha minus I. Okay, so this is just again manipulation of integration by parts, but it gives us an advantage. So what is the advantage? The advantage is I will use this relation here, because this is what I got, that e to the power iux e to the power minus alpha x fx, this integral is actually equal to this thing. I will use this in the Fourier inversion, because in the Fourier inversion is supposed to recover the function inside. So if I apply the inverse Fourier transform on the right hand side here, I should be recovering e to the power minus alpha x fx, whatever is inside this box here. So my recovery formula for e to the power minus alpha x fx should be 1 by 2 pi integral e to the power minus iux as in the inverse Fourier, and whatever was on the right hand side. So I put everything on the right hand side inside here. So then that means capital Fx is just 1 by 2 pi e to the power alpha x, because I can put this on the other side, this integral. So this integral is a single integral. So what we really wanted to achieve was to avoid a double integral. Using the direct definition through the density function, we had to go through a numerical integration twice, which I said is more error prone. To avoid that, we use this trick. So this is like an integrating factor trick in differential equation, similar kind of trick. Here it is called a damping factor. Using that trick, what we get is I can recover fx using a single integral on a Fourier transform, but with a transformed variable. So this transformation is something that we have to choose carefully, because again it is numerical analysis. Choice of alpha will be important. alpha value I have to choose. But we will come to that later. For now, suffices to say that we have been able to avoid a double integral to evaluate the cumulative distribution function. It doesn't sound like a very big deal algebraically, but numerically it is. If you have ever done numerical integration using a computer, you will know that errors get accumulated very quickly. Have you done numerical integration ever in any statistical application?
Sir, we have done Monte Carlo integration.
You have done Monte Carlo integration, but not using typical finite difference or expansion techniques?
We have done those in numerical analysis course 1.
Yes. Trapezoidal rule, the basic numerical integration routines?
Like in most statistical courses,
No.
it was not a very common practice to use numerical integration.
So in statistical courses, you have always gone straight to simulation, Monte Carlo.
Mostly, yes.
Okay, I understand, because models might be very complicated, but we will come back to
I
that.
have another question here.
Yes, of course.
Sir, phi is a characteristic function, but can it take complex values? Like you are writing phi u plus I alpha.
Right, that's a very good question. So
No,
one
wait,
can
what that
show,
means.
that this is a well-defined object. So
Yeah, like expectation is well defined or not. That
sorry.
I was worried about the well defined.
Yeah, absolutely. So one can show that this is a well-defined object, having a complex argument inside the characteristic function. It's a very good question. So this required an answer, and the answer is actually yes, you can do that. You can show that it is still a well-defined object. The only additional complication that you will face is now your integration will become more difficult, but the definition is fine. Was that the question you wanted to ask, or was it something else?
Yes. It was.
Yeah. So I am not, again, so as I said, so in the HITSA culture, I am not going to spend time on that, but I checked that out because this is a very relevant question, whether I can do that actually. And yes, you can. So whatever we are writing here actually makes sense. Okay, so the issue was about avoiding double integrals, and as I said, we will quickly come to those situations where we'll see how much time and computation cost is saved if you can avoid double integrals, and also how much approximation error can be avoided if you can reduce the dimension of integration. And that's why this kind of transformations and tricks are very common in computational areas, not only in finance, everywhere. Okay, so then of course, we all know that we can evaluate all the moments from the characteristic functions. So if I have the nth order derivative, I can evaluate it at 0 and find out the expectation of x to the power n. These results are already known, so I don't need to discuss this in detail. This is just like recapitulating that I can always recover the moments from the characteristic functions. Not only that, it's very important that if I know all the moments, I also know the characteristic function. So there is also the other side of the story. And that's what I emphasized a little earlier, that if you do not know the distribution of the density, but you can evaluate all the moments, from that you can actually find the characteristic function, and that path is an efficient path to the density and distribution. So this part is clear, right? So this all of you know from your undergraduate days. So there is one more thing that we need to use here, because most of the time we look at mean-centered random variables. Even in finance also, we look at mean-centered random variables. So we do not study x itself, we study x minus expectation of x. So what we require is characteristic function of the d-mean random variable. So y is x minus ex, and this is the relationship that we are going to use, that if I want to evaluate expectation of e to the power iu y, y is x minus expectation of x, then I know that that can be written in terms of the original characteristic function of x with an additional factor outside. So expectation of e to the power iuy can be written as e to the power minus mu 5 prime 0. This 5 prime 0 comes from the mean expectation of x into 5. Phi u is the original characteristic function of random variable x. Okay, this is clear.
Yes, sir.
So this will be useful for us. So it is good to just mention this. The other important numerical issue is Jensen's inequality correction. So what is this inequality correction? So remember that most of the time our stochastic process is a geometric Brownian motion in finance. So last term, most of the models we started out with the geometric Brownian motion. So our geometric law is restated here in terms of ST equal to S0, which is stock price at time 0. And then we have e to the power r minus q times t plus omega t plus xt. What is r minus q? R minus q is the mean rate of return on the asset under a risk neutral measure. So these are our standard notations, bank rate, dividend rate, etc. Using them, we find the mean rate of return. Xt is the stochastic process of the underlying return. So xt is like log of st. So xt is the stochastic part of the underlying return, which we will model with some process here. And of course, we also assume for now that we know the characteristic function of the process xt. So phi u is the expectation of e to the power iu xt. That is our characteristic function for the process xt. What is omega? Omega is the mean correction for xt. Because I have not said that x has mean 0 or anything like that. So whatever may be the mean of x, we have to adjust through an additional term. We will see how we evaluate this term so that the expectation of st remains consistent. Under a risk neutral measure, we know that expectation of st has to be s naught e to the power r minus qt. Only the first part. So that is our risk neutral expectation, right? So in a risk neutral world, the expected return can only be equal to the bank rate.
Yes, sir.
Yeah. So that has to be true. That's how actually we found the risk neutral measures. So this omega is essentially the mean adjustment for xt, so that this part does not contribute anything to the mean. So we'll see exactly how these are computed as we go along for different processes. But in general, this would be our canonical model, that this is the bank return, this first term. Then I have the stochastic process, which we are going to use, and the mean adjustment in omega. So of course, we need the characteristic function of the underlying ST process. So suppose I use this symbol psi as the characteristic function for log st, because log is what we are interested in. So then I can write psi u as this whole thing. So I write out st inside, take out the terms which are non-stochastic, which is s naught, r minus q and omega. So I am left with only x inside. So I know that psi u, the characteristic function of log st, will be phi u, the characteristic function for xt, times this mean part. So this is essentially what you can think of as the mean part. So this is in the same spirit as here, this demeaning of random variables here. So this term here and this term here has the same spirit. And again, I use that trick once again. I substitute minus I for u. So again, the same question, is it well defined? And this have been checked, that you can insert complex arguments inside characteristic functions. So if I substitute minus I in place of u, what I will get is expectation of st equal to this thing. So it becomes s naught e to the power r minus qt e to the power omega t phi of minus I. So is this okay? Is this clear?
Yes, sir.
Because if I put minus I here, this term will basically become 1. So that's what I'm using. And I'm allowed to do that. That is something that we just discussed a little while ago. But you should check that I can actually do this. Okay. So then we know that under the risk neutral measure, expectation of st has to be s naught e to the power r minus qt. That's by definition. And comparing this equation and the earlier equation, I can immediately say that e to the power omega t phi of minus I must be equal to 1, which is how we solve for omega. So as I said, omega is the mean correction for xt, but then we needed an expression for omega. We need to know how omega can be calculated. This is how we calculate omega. We use the fact that under this neutral measure, expectation of stock has to be the same as the bank rate. So that I equate with this equation. So omega turns out to be minus 1 by t log of phi minus I. Again, question, log of phi minus I, is it well defined? That has to be checked, but we can verify that it can be defined. So finally, the characteristic function of the log of the process, so log st psi u. Psi u we can write out in total because now I know omega t. Psi u will be e to the power iu log s naught plus r minus qt. So this is the term inside here. Then phi u and then phi minus I whole power I. So this is a sort of very complicated object, but this gives me an explicit form for the characteristic function of the log process, log st process. Of course, I need to know small phi. So as I said, we assume that we know the characteristic function for x. So if I know the characteristic function for x, then I can write the psi u function in terms of phi. So these are transformations that we'll be using repeatedly. This is like our basic toolbox. Okay, so a little bit of more specializing. So suppose I want to talk about the characteristic function of the log of a martingale, because martingales are very important for us. We are always trying to arrive at a martingale so that we can find the expected no change situation. So suppose MT is a martingale and I want to find again psi u. So it's a bit of notational abuse, but I keep using, the book keeps using psi. So psi u is a expectation of e to the power iu log MT. So this is our characteristic function log NT. Again, observe that if we substitute minus I for U, I will obtain psi minus I equal to, so I'll put minus I here, I will simply get expectation of NT. And because NT is a martingale, and this is the unconditional expectation of NT will be M0, value of the martingale at time 0. So this calibration I will need later. That's why we do it right away. That psi of minus I, we evaluate it and keep it with us. Because when we are going to evaluate this whole expression, we will need that. Now, let us look at a standard model. A standard model for log MT. So suppose log MT is NT plus AT. So this is my model where AT is the deterministic part of the process, which is like the trend, and NT is the stochastic part of the process. So martingale need not be both of these things. It can be only stochastic, but in general, I can think of the martingale consisting of one trend part, deterministic part that I want to take out. So I take out the deterministic part. So it is like our usual time series modeling. We break up the time series into components. First, assume that the stochastic component is known. So I know the process, the stochastic components process. But I do not know the exact expression for the deterministic component. So AT, I need to evaluate. Moreover, we assume that for NT, the characteristic function phi n is also known. So I know the process, I know the characteristic function. The characteristic function of NT, that stochastic component, is known. We will use that to derive the deterministic component. So how do we do this? So psi u is our object here that we want to study, the characteristic function of log NT. So psi u I write by definition as expectation of IU log MT, which I break up into the deterministic and stochastic terms, because that's how we modeled it. So I get a product of two terms. One of them I can take out because, as I said, my A part is deterministic, so that can come outside the expectation. And whatever remains inside, I have assumed that that form is known to me, that is phi nu. So this part is phi nu, which is known to me. I have taken out the deterministic part, which actually I want to evaluate. Again, same trick, substitute minus I for u in here. So we'll get psi of minus I as e to the power at phi n minus I. So combining these two equations together, because I know psi minus I is m0, I can immediately write at equal to log of m0 by phi n of minus I. So again, so this is the same trick used over and over. But if I want to evaluate unknown deterministic parts, trend parts, this is a very easy model to handle, provided I know the model for the stochastic component. So the deterministic part in the log martingale here, the log martingale is what we were studying. The deterministic part can be easily evaluated from this trick as this expression. And if we substitute this AT in the final expression for the characteristic function, I can immediately write. So basically this expectation of IU AT I can now write in terms of this equation here. And we can see that expectation of this thing, which is the characteristic function, is phi nu, that is assumed to be known. And the deterministic part which came outside is given by m0 phi n minus I power I. So it is basically the same type of expression as here, with the same purpose. That whenever I have some deterministic part or trend part, I want to take it outside. But to take it outside, I need to know the form, so we derive the form. So later on, when we are doing actual computation, we will know exactly what expression to estimate. All right. So is this clear so far?
Yes, sir.
So it is just using a standard trick. I am separating out deterministic and stochastic parts in the processes because that's what we always do. In some cases, we know how the deterministic parts will behave under risk neutral measure, etc. We use that information. And sometimes if I know the characteristic function of the stochastic part, I can also use that information in turn to evaluate the deterministic part. So I can go both ways depending on what piece of information is known to me. I try to figure out the other part. That's what we do all the time. So these tricks we will be using repeatedly. So now let us look at some standard distributions. Some of the very common probability distributions, you know all about them. So I will quickly review these things. We'll start with exponential distribution. Exponential distribution is very important for us because it gives us that memoryless property, divisibility, all those very nice theoretical results, which are also very important in empirical application. So our notation will be exponential distribution with mean lambda. So the mean lambda means the distribution of the time between jumps of a Poisson process, and the rate will be 1 by lambda. So the density is given by lambda e to the power minus lambda x for positive x. The CDF will be given by this. The characteristic function can be written out immediately using this density as e to the power iux lambda e to the power minus lambda x.
Sir, should not be the other one.
Should not be
Rate lambda is this one.
you mean it should be 1 by lambda?
With rate lambda, that's it.
Oh, you mean this should be rate lambda? Oh, so did I mix it up? So this should be 1 by lambda then, correct?
Yes, sir.
Okay, sorry, thank you. So now I can actually make the changes immediately. So this is correct, isn't it?
Yes, sir.
I get confused with this very easily, this 1 by lambda and lambda business. So, okay. So mean is 1 by lambda, rate is lambda, and that is the density. Thank you so much. So, because this is the density function that is being used, so it should be with the right meaning. Okay, so phi u is this thing, and this is actually a complex integral. So it will need a little bit of knowledge how to integrate this. So I will not get into that again. So we are not going into much of theory, but this can be evaluated, and the expression will be actually quite simple. Phi u will be given by lambda minus iu. So did you actually ever evaluate the characteristic function of exponential distributions?
Yes, sir.
So how did you do that?
In just the integration, this.
But the integration is actually involving complex things, right? So when you learned the characteristic function, did you already know complex integrations? Or did you use some result?
No, we like e to the power I ux, we split it in cos of and sine of, then we use Fourier transformations.
Oh, so you went the long way. Okay. Okay. Trigonometric transformation and then putting them back together.
Yes.
Oh, but that must have been very hard.
Yes, but we did that in
Correctly, you
probability.
did that. Okay, no, that's good. So you know the hard way. Very good. So that will also come in useful later on in this course also. because we are also going to use the trigonometric transformations for some of the numerical routine techniques. Okay, good. So anyway, so the final result, which I'm going to state here directly without going through the pen, is that phi u is lambda by lambda minus iu. That is the characteristic function for the exponential distribution. So now if I try to generalize this to the gamma distribution, you do know that gamma is a generalization, right? Exponential is a special case of gamma. That must be known, correct?
Yes, sir.
Yeah. So the gamma random variable with this PDF with parameters beta and alpha. So these are alpha is shape, beta is scale, etc., etc. So phi u, the definition will be this. And again, if I do the same integration idea, one can find that the phi for the gamma distribution will be given by beta minus iu power alpha. And that also actually explicitly shows the connection between exponential and gamma. So you can just put alpha equal to 1 and you get this form. So that is for the gamma distribution, because there is a definite relationship between them. So this is also explained here. So if alpha is an integer, then I can write this as a sum of exponential random variables with the same beta. So putting alpha equal to 1 means I just take one of them. Just as a side comment, the chi-square distribution is also a special case of gamma. Chi-square is gamma half d and half. And again, it has, obviously, then it has a characteristic function in the same class, and one can derive it as 1 minus 2 iu power minus d by 2. So chi-square with degrees of freedom d is a special case of gamma with parameters half d and half. So the characteristic function here, I can insert the values, relevant values of beta and alpha to get 1 minus 2 iu minus power minus d by 2. So these are the exponential class, which we will be needing later on. So we keep them with us, all exponential, gamma, and sometimes maybe chi-square. So I will just talk about a little bit, talk about the Levy process here, because we introduced Levy process last term in the end to model financial asset prices with jumps. Levy process is definitely more complicated than our usual random variable, usual stochastic processes with smooth properties, nice density functions, etc. But it so happens that financial assets with jumps in their price process is very common. We see a lot of such real life examples now. So studying the Levy process becomes very important. So what is this Levy process? So the class of the Levy process consists of all stochastic processes with stationary independent increments. So obviously even Brownian motions are also special cases. We had, I think, in the examination, we had a question like that. So that Levy-Khinchin theorem, that's the characterization of the Levy process. It's a very famous theorem and very nice theorem. It provides a characterization of the Levy process in terms of characterization of the underlying change process. So what does it say? It states that there exists a measure nu such that for all real u and non-negative t, the characteristic function of a Levy process can be written as expectation of e to the power I z xt, z is the variable, which is exponential t phi z. So this characteristic function can be written as e to the power t phi z, where phi z is explicitly calculated as this expression. So phi z has basically two types of terms. The first couple of terms, I gamma z minus sigma square z square by 2, is essentially the same as normal distribution. This is the smooth part, the part without jumps, the part with the density. Then comes the jump part. So the jump part is modeled in this additional integral. And this additional integral is what differentiates the jump processes from the smooth processes. You have a rather complicated object inserted here because you also need an indicator function where x, absolute value of x is small. We will discuss this more in detail when we talk about the PIDs involved with it. But for now, it is important to know that the Levy process, which we started studying last term, do have an explicit characteristic function, but it's not very simple. So whenever we are going to evaluate the characteristic function of the Levy processes, we will need extensive numerical work because this will require numerical integration here. And this numerical integration is not very simple. The measure nu can also be modeled in various ways. We will see some examples later because this is just an existence theorem, the Levy-Khinchin, but we will need explicit models. We will see explicit models in the later chapters. What we do know is sigma is non-negative. This gamma is a real number, and nu is a measure on the real line such that nu 0 is 0, and this integral has to be bounded. What is this integral about? This is minimum of 1 and x square integrated over the whole of the real line is bounded. So basically, the part between -1 and 1 has to be small enough, and the part outside needs to have sufficiently small probability. So if you look at this, what we are doing is we have an x square function, but we are truncating it at 1. So after 1, it becomes flat. So the integral is essentially the probability measure outside -1, 1. Inside, it's the actual area of the x square curve. So what this theorem is saying that the outside probability has to be sufficiently manageable so that this always remains bounded. So that, of course, puts some restrictions on my choice of the measure nu. So I cannot take any measure as my candidate. There has to be some restriction so that this boundedness is maintained. Okay, so I will stop here today. If there are any questions, we'll take them. Otherwise, we'll finish today. Yeah. Any questions at this point? Okay, all right. So if there are no questions, then I have something to tell you that again, as in the last semester, start reading the textbook immediately because there are many details which I am omitting. There are many additional examples that I am not talking about, which would be important to know. So start reading the book. Look at whichever sections are mentioned in the syllabus. So I don't want you to read the whole book like that, but the sections that are mentioned in the syllabus, you should read. So start doing that, and let's meet day after tomorrow at 10:30.